we talk about implementing the various protocols in Python, one of the things that we commonly see is that we implement these in terms of either that same protocol applied to a constituent object or that protocol applied to some base type. Well, what if we have a more complex inheritance hierarchy? And what if it may be ambiguous on first notice, or what if it may be unclear at first glance what it means to apply that protocol to a base type? Here you can see an example of a classic diamond hierarchy. We have 4 types, and they form a class hierarchy with A at the root, B and C deriving from A, and D multiply deriving from B and C. And in each case, we have some method that delegates to the supertype. Now, in the case of A, since there isn't anything higher up than A other than, say, the base object, the behavior that we'd anticipate seeing if we called A.foo, pretty straightforward. In the case of B and C, we'd probably anticipate seeing B.foo and C.foo. And in fact, we can create instances of each of these types, and we can see what the behavior is. If we had W.foo, which is of type A, we'd anticipate just seeing A.foo. If we did the same thing for X or Y, we'd anticipate seeing B.foo and A.foo. In the case of Y, which is of type C, we'd anticipate seeing C and A. The question is, what happens when we do the same for D? And this brings us to probably our favorite Python nursery rhyme. It's a nursery rhyme which I'm sure you sang when you were in school, playing on the playground with the other children as a reminder for how object orientation in the diamond hierarchy works. Let's take a look. In Python 2, there used to be the so-called old-style classes, which was an attempt at object orientation that, frankly, didn't quite get the details right. And Python 2 introduced new-style classes about halfway through its time. And new-style classes were an attempt to fix certain characteristics of the original implementation of object orientation that just ended up creating all sorts of thorny bugs. One of the things that new style classes introduced is what's called C3 linearization. The idea that we have a class hierarchy and a method by which we can resolve where an attribute comes from when invoking the get attribute protocol. And we can do that in a way that's consistent and in which multiple inheritance is ensured to provide us a consistent and unambiguous answer. In this particular hierarchy, we can think that we have D that derives from B and C that derive from A, and what we want at each step along the way is that the order in which we look at the base types are always a subset of the order in which you look at the base types at any higher level. There's always some linear, unambiguous ordering. In other words, at D, we can see we derive from B and C. From the perspective of B and C, we derive from A. And so from the perspective of B, it can think, well, the order is B first and then A in terms of where you look for things. From the perspective of C, you can think, well, the order is C first and then A in terms of where you look for things. And thus, from the perspective of D, what could the order be? Well, we can form a linear ordering based on the ordering that you see we derive from B and C. In other words, we could say the ordering should be D, B, C, and A. In this particular perspective, all of the relationships at all of the base levels are preserved. The linear ordering is preserved at every base level. B says, well, you know what? You always look here before you look in A. C says you always look here before you look in A. And D says, okay, thus we can look in B, C, and then A. And this gives us our method resolution order. And in fact, we can ask the type D, what is your method resolution order? And it will tell us D, B, C, and A. As you can see, the order in which we specify these will affect this method resolution order. If we say D inherits from C and B, then a consistent ordering would be D, C, B, and A, because at each level, D says, well, C must come before B. At B's level, B says B must come before A. At C's level, C says C must come before A, and so you can linearize these. There may be cases where you are not able to linearize these. For example, if this wasn't exactly a diamond hierarchy, but, for example, D tried to inherit from A, well, here D is saying A has to come before B, but B says, well, B has to come before A. There is fundamentally an incompatibility here between the linear orderings that we see, and as a consequence, Python will refuse to create these classes. Python will say there is no way to create a consistent ordering for these. There's no way to create an MRO for these. Well, one thing that you can think is every time you perform an attribute lookup in Python, you follow the MRO. And so if we wanted to write our own version of getAttribute, one of the pieces for that would be you first look in the instance state. If you don't find something in the instance state, then, as you said multiple times playing on the playground, you row your boat gently up the type hierarchy, going to each of these base classes in the order that the MRO specifies. That's what the MRO is. This is what new style classes, or one of the many things that new style classes introduced in Python 2. And as Python 3 programmers, this is the view of classes that we have to deal with. This is our model of object orientation that has stood the test of time. This is how we determine where an attribute comes from in the case of inheritance or in the case of multiple inheritance.